Okay, welcome back. This is video lecture 25.3, and we're going to talk about sections 4 and 5 in chapter 25, starting with section 4, where we come to grips with the fact that an electric field contains energy, just in its own right. An electric field contains energy, or if you like, it's stored energy. So, when we charge up a capacitor with plus Q on one conducting plate and minus Q on the other conducting plate, we know we create a nice uniform electric field, if it's parallel plates, in the region between the plates, and that electric field therefore has stored energy, so there must be energy stored in a charged capacitor. I demonstrated that in class by showing you that a charged capacitor could be used to light a light bulb. So we know that a charged capacitor stores energy. It might be very important then to be able to calculate how much energy, in joules, a charged capacitor has. And that's what this section is getting at. We're going to do a thought experiment to figure out how to do this. We start, of course, with an initially uncharged capacitor, and we're going to bring it to a final charge Q. And we're going to do it in a thought experiment by moving electrons from one plate to the other. So just imagine the two parallel plates, for parallel plate capacitor, and we're going to snatch an electron from one plate. I'll do it the reverse way, pardon me. We'll snatch an electron from one plate and move it down to the other. In so doing, I'll leave the top plate with a plus charge, and I'll start building up a negative charge on the bottom one. And I'll just keep doing that to charge up my capacitor. It's a thought experiment. Okay? And so that first electron is easy to move because the plates are uncharged. But after that, it gets a little bit harder and a little bit harder to move an electron from top plate to bottom plate because the bottom plate's getting more and more negatively charged. It already has excess electrons, doesn't really want many more. If I'm going to put an excess electron on the bottom plate, I'm going to have to push it onto that plate. I'm going to do work. And much like I can do work to compress a spring and give it stored energy, I can do work here on charges and give a charged capacitor stored energy. So as we imagine doing this experiment, moving electrons, then the magnitude of the charges on each plate increases. The top plate gets more positive, the bottom plate gets more negative. The electric potential V, or potential difference, between the plates gets bigger. The magnitude E of the electric field in the volume between the plates increases, right? The volume between the two plates, right, roughly like that, where the electric field is. The electric force opposing my transfer increases. And the work that I have to do to transfer an electron from the top plate to the bottom plate increases. All right, so now, how are we going to get a formula, though, for calculating what the total work is I had to do to charge up a capacitor to its final charge amount, Q? Well, we're doing a thought experiment. We imagine some intermediate stage during the charging when the charge on either plate, magnitude, is just some number Q prime. It's not quite the final yet, and it's not the initial of 0. It's somewhere in the middle. And the corresponding potential difference is some value V prime. And with that configuration, I'm now going to transfer a tiny amount of charge more, dQ prime, from one plate to the other. The work I have to do for this transfer is, using the idea that electric potential is electric potential energy per unit charge, is I take the potential difference between the plates V prime times the amount of charge I want to move, dQ prime. And that'll be the work I have to do, dW, for that little transfer. So now I can calculate the total work to transfer all the charge. I'll do it right here. I'll just call it W. And I'm going to add up all the dWs, all the little bits of work I had to do to transfer the little bits of charge, dQ prime. So for the dW, I used that formula, V prime, dQ prime, and I'm adding up all the V prime, dQ primes. But now I substitute from Q equals CV. I'll put that over here. Q prime is C V prime, C is a constant, that V prime is Q prime over C. And I put that into the integral for W. Q prime over C dQ prime. And the limits on the charge are 0, because that's what we started with, nothing. And the final charge on the plates is Q. I can bring the 1 over C out front. The capacitance is constant. So the integral from 0 to Q, Q prime dQ prime. Don't be thrown off if that integral looks weird to you. That's just an integral of the form x dx, which is x squared over 2. And then plug in the limits of Q and 0, and you get Q squared over 2C. And that's the total work I had to do to charge up the capacitor. And much like the work I do to compress a spring shows up in its potential energy, the work I had to do to charge a capacitor shows up in its potential energy. So now we just write that as U, the stored energy, the stored electrical energy, in a charged capacitor, U cap. It's the final charge squared over 2 times the capacitance. And that's a handy formula. That's how we can find out how much stored energy in joules is in a charged capacitor. I need to know 2 things. What's the final charge amount, Q, and what's the capacitance? And so that's what this statement right here says. The stored electrical energy in a capacitor with capacitance C and total stored charge Q is U cap equals Q squared over 2C. Very handy. This is for, but please note, this is for a charged capacitor. Now, there are other versions of this formula that are just handy to know about, okay? And they come from combining the answer we just got with Q equals CV for a capacitor. So what I can do, for example, is I can substitute Q equals CV in the U cap formula where the Q is. So Q squared means I'd have C squared, V squared, and then I have over 2C. 1 factor of C cancels there, and I'm left with 1/2 CV squared. Okay, right here. Or I can take the answer I just had, that I have, U cap equals Q squared over 2C, and I can substitute something slightly different. Q squared over 2C, C equals Q over V. 1 factor of Q cancels, that V goes upstairs, and I have 1/2 QV. So you end up with these 3 formulas that all say the same thing. They give you a way to calculate the stored energy in a charged capacitor. Q squared over 2C, CV squared over 2, and QV over 2. They all say the same thing. Which form we use in a given problem, just based on what we are given and what we're asked for. Now, as I've said, this stored energy, you can think of it as it being actually contained in the electrostatic field that's been formed between these charged plates. Okay? The stored electrical energy is contained within the electrostatic field between the plates. I want to show you that now. Here's our schematic, a typical schematic of a parallel plate capacitor. Top plate has plus Q. There, overall. Bottom plate has minus Q overall. The areas of the plates that are facing each other is A. The distance between the plates is D. We'll take the space between the plates to be completely empty. The formula for the capacitance of such a parallel plate capacitor is C equals epsilon 0 A over D. We get a nice uniform electric field E in between the plates. And that's what these field lines here are showing. Nice uniform electric field, E, magnitude between the plates. And so you can use this wonderful formula to calculate the potential difference between the plates. And I just want the magnitude of it. And because the electric field is uniform, the delta V magnitude ends up just being the magnitude of the electric field times D, the distance between them. This is a very handy little formula for the magnitude of the delta V if you have a uniform electric field. Okay, so now I'm going to use that in the formula U cap equals 1/2 CV squared. Okay, here we go. U cap equals 1/2. Here's the formula for C, epsilon 0 A over D. Here's the formula for V, electric field times the distance, squared. Don't forget that. And what you end up with is epsilon 0 A D E squared over 2. So it's a way to write the stored energy yet another way for a charged capacitor in terms of the electric field between the plates. Note the squared on the factor of the electric field. That's important. And we don't use that often, but it's still helpful to know that. But here's what is really a helpful result here. We're going to define somewhat of a new quantity here. But we know in physics we like densities, don't we? Densities. Something per unit something. Something per unit length. Something per unit area. Something per unit volume. Right? Linear charge density, surface charge density, volume charge density, mass density. How about energy density? For what? For the electrostatic field. And all we mean is energy per unit volume. The symbol for energy density, watch the notation carefully, is a lowercase u subscript e. Okay? Energy density of an electrostatic field. That's the symbol for it. It's defined to be the total stored electrical energy over the volume containing the electric field. Total stored electrical energy over the volume containing the electric field. Let's apply that to our parallel plate capacitor. Let's get the energy density in that electric field, little u sub e. Okay, the stored energy here, so it would be like this, little u sub e. Big U cap, the total stored energy over the volume between the plates. VOL stands for volume. So here we go. For little u sub e in the numerator, there's big U cap, epsilon 0 A D E squared over 2. And then the volume containing the electric field is that space right up there between those two conducting plates. Well, that's just an area A times a distance D. And then when you do that, you'll see the factor of A upstairs and downstairs cancels, and the factor of D upstairs and downstairs cancel. And you end up with a pretty simple formula for the energy density of an electrostatic field. 1/2 epsilon 0 times the magnitude of the electric field squared. Note that this would be in the SI unit of energy, joule, over volume, meter cubed. And although I derived this for the particular case of a parallel plate capacitor, this is a completely general result. It is the energy density associated with any electrostatic field. Okay? All right, let's do a little bit of practice together. We'll just do this together, okay? To practice with this idea of stored energy in a charged capacitor. Okay, we have two capacitors. We're going to label them 1 and 2. They're identical except that capacitor 1 has twice the plate separation compared to capacitor 2. D1 is twice D2. Let's draw it. Parallel plate capacitors are easy to draw. There's capacitor 1. Okay? Each plate has area A, and the distance between them, D1. Capacitor 2 has the same area plates, A, but the distance between them, D2, I tried to get it right, is half the distance compared to capacitor 1. All right? Note then the regions where, and they're both charged up to an amount of charge Q1 on this one, and Q2 on this one, and we're told that the Q's are equal. Note the volume then where the electric field is in each case is the volume between the two plates. So that would be that volume for capacitor 1, and that would be the volume for capacitor 2. All right, first question. How do the magnitudes of the electric fields between the plates compare? Is E1 less than E2? Is E1 greater than E2? Or are the E's equal? Well, here it's just helpful to remember a very useful result that we've already derived using Gauss's law for this geometry. And that is that the magnitude of the electric field in the region between these two plates is Q over A epsilon 0. We got that from Gauss's law. Q on either plate, this is just magnitude, over the area of the plate times epsilon 0. All right, now let's compare for the two plates. They have the same Q, and we're told they have the same A. So they must have the same electric field magnitudes. Okay, so it must be C. All right, next. How does the volume labeled VOL for capacitor 1, volume between the plates, compare with the volume VOL2 of capacitor 2? Okay. How much volume between the plates? How do they compare? Well, the volume between the plates is pretty straightforward. It's the area times the distance, d. Now, the two plates have the same area, but they do have different distances, don't they? D1 is twice D2. So it must be that the volume in 1 is twice the volume in 2. Right? There's twice as much volume between the plates of capacitor 1. So, B. And then lastly, C. How does the potential energy, stored energy, U1 of capacitor 1 compare with the potential energy U2 of capacitor 2? Well, given how they've set us up here comparing E's and volumes, the formula I am going to use for the stored energy in a capacitor is the expression from the previous slide, epsilon 0 A d E squared over 2. All right, now they have the same A, they have the same E, right? But they have a different D, where, as we know, D1 is 2D2. So U1 must equal 2 U2, since U just depends on D. So B again. So capacitor 1 ends up storing more energy because it's got more volume to put the electric field in. Okay, so that's some practice with the energy of a charged capacitor. We'll be doing some homework problems with that. But now I have one more topic I want to talk about. Chapter 25, Section 5. And it is the last section in this chapter that we're going to discuss. And it is pertinent to what you have been doing in lab this week, where we're going to talk about taking the plates of a capacitor, and instead of having emptiness between them, which is often called vacuum, we're going to insert an insulating material. And in this context, the insulating material is called a dielectric. And we'll have to talk a little bit about that name. Okay, so we're going to talk about a capacitor with a dielectric material. That means, well, just what we say right here. A capacitor with insulating material inserted between its two conducting plates. And the big question is, why would you insert an insulating material between the plates of a capacitor? What do you gain from doing that? What happens physically when you do that? That's what we're going to talk about. But it turns out to be convenient to be very explicit about the conditions we're going to talk about. So I have here what I call case 1. And we're going to fix the charge on the plates. I'll explain how. So we start with an empty capacitor. That means nothing between the plates. And we charge it up with a battery or a power supply to a potential difference V0. And that means we have a charge Q0 equals C0 V0, and we have a formula. C0 is epsilon 0 A over D. And right here then is the circuit on the left that shows that. We have the empty capacitor. Nothing between the plates. We charge it up with a battery or a power supply, so there's plus Q naught on the top plate, minus Q naught on the bottom plate. It's got a capacitance C naught, which is epsilon naught A over D. And the device it's connected across is called a voltmeter. And it's reading some voltage, V initial, V naught. Now, voltmeters have an important property. Their internal impedance, which is like resistance, is extremely high, intentionally. And that means that even though the voltmeter is connected right across the plates of that capacitor, it's not going to allow any charge to bleed through it from the plus plate to the minus plate. So the charge on the plates of the capacitor is fixed. It can't go anywhere. And that's important to understand here in this little experiment. All right, and that's what it means when it says, isolate the capacitor so that the charge on its plates cannot change. So whatever battery or power supply I used to charge it up when it was empty, and give me that charge Q naught, I've now disconnected that battery or power supply. It's gone. It's out of the picture. I do have that voltmeter across it, but it's not going to allow any charge on the plates to move. That's what we mean by isolating the capacitor, okay? And so that the charge on the plates is fixed. Charge on plates is fixed. And very important to remember that. And now, under that condition, we're going to insert a sheet of dielectric material. Dielectric is just a fancy name for insulating material. In lab, you use those acetate sheets, which is a kind of a plastic. Okay? Any insulating material, plain old paper, wood, most wood, right? Anything that's insulated. That's the key thing, insulated. But it's called dielectric material. Put it in there between the plates. That's what the picture shows right there. It's that rectangular chunk of material shaded in a kind of an orange. When you do that, think of it as an experiment. When you insert that dielectric and you fill up that space between the plates, a very interesting thing happens. The reading on that voltmeter decreases. The potential difference across the plates decreases to some new value V, where V is smaller than the V initial. That is what you learn from experiment, okay? Or V final, I guess is what I'm calling it. So let me label it V final, okay? All right, so measurements show that the potential difference between the plates decreases to a new value. Here's the key thing. V final is less than V initial, smaller. Now, because the charge on the capacitor is fixed, here's what we can do. We can start by equating Q initial to Q final. The charge is fixed. For Q initial, look at the picture on the left, we have C initial, V initial. For Q final, I have some C final times whatever the V final is on the voltmeter. Now just cross multiply. C final over C initial equals V initial over V final. Note the order. And V initial is larger than V final, so this is bigger than 1. What does that mean? Here's the key thing. C final is bigger than C initial. By inserting the dielectric, I have made the capacitance larger. Inserting the dielectric, makes the capacitance larger. And now you know why we use dielectrics. It makes the capacitance larger. Okay? Now we're going to introduce a new quantity. Very convenient. It's called the dielectric constant. And it's a property of the dielectric material. Okay? And here's how it's defined, and here's its symbol. Be careful, it looks like a K. It's not. It's a Greek lowercase kappa. It's defined to be the final capacitance over the initial. Okay? That's it. Now, if we have the case where the dielectric completely fills the space between the plates of the parallel plate capacitor, then you can take that little formula up there. You can certainly just rearrange it to that. Let's just drop the final subscript, and you see that the C then becomes kappa times the C you had when it was empty. But the C empty is epsilon 0 A over D, so the whole thing is kappa now, epsilon 0 A over D. And inserting the dielectric has increased the capacitance by the factor kappa. And again, that's why we put dielectrics in there, to get a larger capacitance. Note from the definition up here that kappa, dielectric constant, is a dimensionless quantity for a given material. It's the ratio of two things that have the same units. There are no units on kappa. Kappa is exactly 1 for vacuum. Now over here I've got a table of dielectric constants for different materials. And the very first entry is air at 1 atmosphere pressure. And the kappa there, I'll just read it, 1.00054. That is so close to 1 that we'll go ahead and approximate the dielectric constant for air to be 1. And then for pretty much any other insulating material, the kappa is going to be bigger than 1. And they list some dielectric materials over here. Polystyrene, paper, transformer oil, Pyrex, mica, porcelain, silicon, germanium, ethanol, water at different temperatures, titanium ceramic, strontium titanate, and so forth. Notice as you go down, these dielectric constants are getting pretty large. Strontium titanate is a dielectric constant of 310. So depending upon what kind of dielectric material you insert between the plates, you could really end up multiplying the capacitance by a lot. And that's in fact the secret to getting a capacitance that's big. Like I showed you in class, the 1 farad capacitor, which was about that big. And I talked about how in the old days, we would have never talked about a 1 farad capacitor. It would have been impossible to get that much. We would have been talking about microfarads, for example. But advances in material science have enabled us to create dielectric materials with very large kappas. Very large. And that's the secret to getting a capacitor with a capacitance of 1 farad. Use a dielectric material with a large dielectric constant. Now remember that experiment showed us that when we inserted the dielectric, the potential difference between the plates decreased. Okay? Let's figure out by what factor the potential difference decreases. Let me remind you of a formula we had just a slide or so ago. C final over C initial equals V initial over V final. And now let's rearrange and solve for V final. V final equals V initial times C initial over C final. But C initial over C final is 1 over kappa. So here's the thing. V final is V initial over kappa. Remember, kappa is greater than 1. Well, greater than or equal to 1. Okay? But for anything, really, it's bigger than 1. And so V final is less than V initial. As the experiment showed, and it's less than V initial by the factor kappa downstairs. Right? So the potential difference is reduced by a factor kappa. Here's another question. What happens to the electric field between the plates when the dielectric is inserted? I'll need this result for a uniform field. That the potential difference between the plates is the magnitude of the field times the distance. Let me use this result we just found. V final equals V initial over kappa. V final is E final times D, the final electric field times the distance between the plate. V initial is E initial times D, the initial electric field times the distance between the plate. The factors of D cancel, and I get this result that tells me the final electric field is the initial electric field over kappa. So the final electric field is less than the initial. Okay? The electric field magnitude is decreased when the dielectric is inserted between the plates of the isolated capacitor. And that's an important result. I'm going to show you physically why that happens in just a minute. Okay, for the isolated capacitor, the capacitance gets bigger, the potential difference between the plates gets smaller, and the electric field gets smaller. Here's another question. What happens to the stored electrical energy of the capacitor when the dielectric is inserted? I'm going to need this result. Stored energy in a charged capacitor, Q squared over 2C. So U final is Q final squared over 2C final. But remember, the Q is fixed, so Q final is equal to Q initial. But C final is kappa times C initial. But then Q initial squared over 2C initial is U initial. So U final is just U initial over kappa. U final is less than U kappa. The stored energy has decreased. Here's an interesting question. Where did the lost energy go, quote unquote lost? Right? If U final is less than U initial, I have less stored energy than I did before. Where'd that loss go? Well, something happens that is not immediately obvious, but experiments would show. When you take that isolated capacitor with its two plates, one plus and one minus, and you start to insert that dielectric between the plates, you will discover that there will be an attractive force on the dielectric from the electric field between the plates of the capacitor. And the dielectric will literally get sucked into the capacitor by the capacitor. And that means it's going to do work. It's going to use some of its stored energy to do work to pull in the dielectric. So you're converting stored energy into kinetic energy. Now I want to give you a little bit of a physical explanation as to why the electric field magnitude gets smaller when you insert a dielectric into an isolated capacitor. So here you have on the left a schematic drawing of a rectangular shaped slab of dielectric material. And right now it's completely isolated. There's nothing going on, there's no electric field. Okay? All right. Now, insert this dielectric material, it's just the right size and shape, between the plates of this charged isolated capacitor here, with the left plate positively charged and the right plate negatively charged. And the charge on the plates creates an electric field away from the positive plate towards the negative plate, and they call that E initial. But something interesting happens to the dielectric. It's made up of a whole bunch of molecules, of course, and they're now immersed in this electric field E0. And that ends up having a distorting effect on the molecules. In a way here that's drawn, although it's exaggerated, so that they're distorted, so that the right side of each molecule is a little bit more positively charged, and the left side is a little more negatively charged. You have created a whole bunch of little electric dipoles, and they're lined up the way you see them. Now, in the interior part of the dielectric, you've got positives and negatives right up against each other, and there's no net effect of that, what's called polarization of the dielectric. But over on the extreme left edge of the dielectric, you've got a bunch of negative charge lined up. And over on the extreme right edge of the dielectric, you've got a bunch of positive charge piled up. Okay? And so now, and that's not compensated by anything. So now you've got negative charge, you've got negative charge on the left side of the dielectric, and you've got positive charge on the right side of the dielectric. Some. Well, that itself creates electric field, but directed away from the positive charge. And that's this electric field right here, labeled E. Let me be more careful. E prime, they call it. Okay? Now that's due to that, what's called bound charge of that dielectric. But the key point is that E prime is exactly opposite in direction to the E0 from the charge on the plates. And of course, what actually exists in the space between is the net electric field, the net field, which is the vector sum of E0 and E prime, which is just this little bit left over pointing to the right. And that's why the field is reduced, because that's the E final right there. And the E final is smaller than the E initial because of the effect of that bound charge in the dielectric. That's just the physical reason why the electric field gets reduced between the plates of a isolated capacitor with a dielectric in there. Now the last thing I want to do, just one more thing, is talk very briefly about a second kind of experiment that you can do with a dielectric and a capacitor. Okay, I call this case 2. And in case 2, what we're going to do is fix the potential difference between the plates of the capacitor. Here's how we're going to do it. We start with an empty capacitor. Charge it up to a potential difference V0 with a battery. Okay, we could even draw the circuit. Got a battery. Hook up an empty capacitor between the plates of the battery. This battery produces a potential difference of V0. And that's its one job in life, the battery. That's what it will produce, a potential difference V0 across its two terminals, no matter what you've connected across. And of course then the charge on the empty capacitor, Q0, is C0 times V0. C0's the capacitance when it's empty. Okay, now in the experiment, the next thing, keep the battery connected to the capacitor. Keep that there. That tells you that the potential difference is fixed at V0. It cannot change. Now, insert the dielectric with dielectric constant kappa between the plates. Okay, so now fill up that space between the two plates with dielectric material with dielectric constant kappa. But keep the battery connected. The battery will then keep the potential difference fixed at V0. But we already know the capacitance increases because of the dielectric to a new value C equal to kappa times C0. And so what has to happen is the charge on the capacitor has to increase. Here's how you can see that. Take the original equation up here, solve it for V at 0. V0 equals Q0 over C0. But V0, that's initial, must also equal Q final over C final. If you want to put little final subscripts on these, you can. Q final over C final. Final meaning after the dielectric is inserted. And now just cross multiply. Q final over Q initial equals C final over C initial. But that ratio is kappa. And kappa is bigger than 1. So Q final is now bigger than Q initial. So the Q is not the same now. When you insert the dielectric in this second case, you get more charge on the plates. Where'd that charge come from? Well, it was pushed in place by the electric field set up by the battery in the wires. You can even see that the stored energy increases. Here's the initial stored energy. We'll use that form. U initial U0, 1/2 C0 V0 squared. What's the final stored energy? 1/2 C final, I'll put F's, V initial squared. Remember the V's fixed. So the ratio U final over U initial, well, just divide them, is still C final over C initial, which is still kappa, which is greater than 1. So U final is greater than U initial in this case. So here's a question. Where'd this new energy come from? I gained energy, yes? Had to come from somewhere. Where'd it come from? Well, there's the battery there. Okay? That's pushing charge onto the plates. The battery's doing work. That gives you energy. Okay? All right, so that's the last section of chapter 25. There will be a class video that goes with this where we'll practice with these ideas, and then we'll be moving on to chapter 26. And that's all for this video.